Hello friends, welcome to engineering tutorial. So in the previous video we just got introduced to the second order control system, and we discussed the various terms associated with the second order control system, the characteristic equation, and various other things such as the damping ratio, the natural frequency of oscillation, and the concept of damping. That is, what is an underdamped system, what is an overdamped system, what is a critically damped system, and what is an undamped system. So in this video we are going to discuss the output response of a second order system for step input for the underdamped case. Okay, I am choosing this particular case because it is of very significant value, because all the questions and in every textbook you will find this case is always mentioned, and the output response is always important, and various other the parameters associated with this time response specification is always calculated from this case especially. So what is this particular case? It is the output response of a second order system for unit step input and for underdamped case. Okay, underdamped condition. Okay, underdamped condition means the damping ratio zeta is lesser than 1. Okay, the damping ratio zeta is lesser than 1. Also, if you consider this as delta, as damping ratio, write the damping ratio as delta, that is lesser than 1. Okay, so this is the particular case. So we'll discuss this. Now let us just see what is the output response for the particular condition that we just wrote it down here. So we know that this is the closed loop transfer function for a second order system. Output by input, Laplace transform Cs by Rs is equal to this: omega n square, natural frequency of oscillation, the square of that is square, plus 2 zeta omega ns plus omega n square. Okay, this is the transfer function, the closed loop transfer function. Now we know that for unit step input, okay, for unit step input, the Laplace transform is equal to 1 by s. So here Rs is equal to 1 by s. So Cs will become omega n square by s square plus 2 zeta omega ns plus omega n square into 1 by s. Okay, now I would like to tell you something, that this derivation process for the second order system, it's very lengthy, and it has some tricky and complex steps in between. So I will not be deriving here. I have created a PDF file and I have given the link in the description. So if you want, and I would recommend you to please download that PDF file where there is the whole derivation, the mathematical derivation, to get the output response for this particular case, second order system, unit step input, underdamped case. Because if it is a 2 or 3 or 4 page derivation. Okay, so if I do this here in the whiteboard, there is a high possibility that you will get confused and you will not get a hold of how this is working. So you please download that PDF document and see the whole detailed derivation of the output response. Okay, so here I will just directly write the output response and then we'll discuss about some other important things. Okay, so let us just directly write the time domain output response for this particular case, that is the second order system to unit step input for the underdamped case. So the output response is written as Ct is equal to 1 minus e to the power minus zeta omega n t by root over of 1 minus zeta square sine omega dt plus phi. Okay, so this is the output expression. So here we are acquainted with the terms zeta, it is the damping ratio, omega subscript n, which is the natural frequency of oscillation. The two new things that appear here in this equation are omega subscript d and this phi. Okay, these are the two new terms. Okay, so let us just discuss about them. Okay, so you note down these expression. Okay, I'm going to erase it. So where does this omega d and phi come from? So for that we have to draw the damping ratio triangle. Okay, it is called as the damping ratio triangle. It will be a right angle triangle. Okay, so it looks something like this. Okay, now this base is zeta omega n, this is omega subscript d, which is nothing but omega n into root over of 1 minus zeta square, and using Pythagoras theorem, this hypotenuse, it will be the square of these two sides root over, which will be simply omega n, and this angle is phi. So this omega d is actually called as damped frequency of oscillation of the system. Okay, it is called as damped frequency of oscillation of the second order system. Okay, which is equal to omega n into root over of 1 minus zeta square. Now here there are various things that we can calculate using the trigonometric laws. First important thing is cos phi. Okay, cos phi is nothing but base by hypotenuse, which is zeta omega n by omega n, which is simply equal to zeta. Okay, sin phi is perpendicular by hypotenuse, which is omega n into root over of 1 minus zeta square by omega n, which is root over of 1 minus zeta square. Okay, now tan phi, okay, tan phi is equal to perpendicular by base, which is omega n root over of 1 minus zeta square by zeta omega n. Okay, so which is simply equal to root over of 1 minus zeta square by zeta. So you just know how to use these expressions, because we will be using it while solving numerical problems associated with time response analysis. It will come in handy at that point. So you remember this damping ratio triangle. Okay, it is very important. Which one is the hypotenuse, which one is the base, which one is the perpendicular, the trigonometric laws applied with respect to it. Okay, so you remember this. So now let us draw the output response for this particular condition. Okay, the second order system to unit step input for underdamped case.